Hello, I'm Monik. I will participate in this first round and try to explain what I'm doing, how I'm solving problems. In problem A, we are given a string. We need to double each letter and then rearrange the result such that the resulting string is a palindrome. Well, we can just concatenate the initial string with the reverse string, and that will be a palindrome, obviously. Kind of a weird problem, but okay. I guess it would be easier with strings. Okay, yeah, let's use strings. Don't even need to know the lengths. I don't need anything. Just read the string, copy it, then reverse the second one, and then answer the concatenation. In problem B, we need to find a sequence of n integers such that their XOR is equal to their average, as the title says. If n is odd, we can just can there be 0? Can they be equal? Yeah, they can be equal, but can there be zeros? Oh, from 1 to... okay. If n is odd, we can just repeat the same integer n times, and then their XOR will be equal to that integer, and their average will be also equal to that integer. Otherwise, well, I guess if we will group our integers in pairs such that XOR in that pair is equal to the sum in that pair. No, that doesn't work because we will divide by n. No, that doesn't work. Yeah, but what's the solution for n equal to 2? We want XOR to be twice as small as the sum. So like 1 and 3 works, right? The sum is 4, XOR is 2. Okay, so if we will group them in groups of 2, and then n became odd, then we can use the solution for odd n. Just repeat that group n divided by 2 times. So if n is like some power of 2 multiplied by some odd number, if we can solve for that power of 2, then we can just repeat it the needed number of times, and like that won't change XOR and won't change average, so that works. So we only need to solve for powers of 2. How to solve 4, for example. So how did I get 1 and 3 for n equal to 2? Well, let's look at binary, obviously, because we are working at we are thinking about XOR. So if there is 1 in XOR, in binary, so let's say that I wanted like this XOR, then the sum should be 2 times bigger, so we just shifted by 1. How can that happen? Well, we know that in this bit we want to have odd number of ones, so like 0, 1. And in this bit we want to have even number of ones, so either 0, 0 or 1, 1, and 1, 1 gives us the sum we want. Okay, cool. How to do something similar? With n equal to 4. So let's say I want to get XOR that will be just power of 2. So XOR will have 1 here and nothing else. Then the sum should have only 1 here and nothing else. We already have 1 here, and actually we can like add 2 ones here to increase the sum, but the XOR will stay the same. So now we only need to get like another 1 here to get 4 times this bit, and this is done just by adding a lot of ones here. Like we know that this multiplication, like we here multiply by n, but we also have n numbers, so we had n minus 1 numbers here, so we just we want 1, so we move 2 positions back and put 1 everywhere. Okay, that works. If n equal to 2 to the power of k, then this distance is k, so we will output 1 and 2 to the power of k plus 1 n minus 1 times. Then the sum is 1 plus 2 to the power of k plus 1 repeated 2 to the power of k minus 1 times. That's 2 to the power of 2k. And XOR is, well, every 2 will disappear, so it's just XOR of 1 and 2 to the power of k plus 1, so it's just 2 to the power of k, and we can see that, yeah, this is n times bigger, so the solution is we're finding this k, so we're finding the maximum power of 2 that divides n. While n is divisible by 2, we divide it by 2 and increase k by 1. So the original n is n multiplied by 2 to the power of k, and then we should repeat the solution for 2 to the power of k n times, and divided by 2 to the power of k. So we write and the solution for k is just 1, and then repeat 2 to the power of k minus 1 times 2 to the power of k plus 1. Let's check that it works when it's not just odd and not just power of 2. So for example, for 10, we should 5 times repeat the solution for 2, which is 1, 3. Looks great. In problem C, we are asked to construct a permutation that starts with number x, ends with number 1, and for everything in between, the number is a multiple of I, of the position. And we want to find lexigraphically minimal such permutation. That sounds kind of stupid. So here are our positions. So on position n we have to put 1. Position 1 we have to put x. What can we put on position n minus 1? Well, we can put n minus 1, 2 times n minus 1, 3 times n minus 1, and so forth, but well, for big enough n, 2 times n minus 1 is already greater than n, so it won't be a permutation of numbers from 1 to n, so we have to put n minus 1 here, unless 2 times n minus 1 is actually not greater than n. So what about the next one? Again, we have to put n minus 2 here, unless we can put something greater, but something greater is only n. So we will just move down until we get some number that is a divisor of n, so we can put n, like up until that number we have used all the numbers here, all the positions, so we can put on position p, we can put either p or n. Everything else unused is just smaller, so that it can be a multiple of p. Okay. But there is also x here, so it can happen that we have not reached or we have reached x and that didn't happen yet. Then we have to put x here, but it is already used here, so this is just bad. If the first time it happens in position x, then we just put n there and then put p in position p, and it will be lexicographical minimum. I'm not sure if it's said, but yeah, we have to construct the lexicographical minimum, minimal such permutation. To construct something lexicographical minimum, we have to put the minimum number in the first position, then second position, then third position, but we have to put 1 here and we have to put x here. So for position 2 the minimum number is 2, for position 3 it's 3, and so on. So what will happen if the first time we can put n instead of p on position p? It's greater than x. Well, after we do that, we have used n, and we will continue the same process, but now free number is p, and we just, well, basically solving the same problem going forward. So, well, backwards. So we can show by induction that the solution exists only if that free number is divisible by x, by this number, because, well, each time we do something, our free number changes to some divisor of it. In the end, we have to put the free number on position x, because we can't put x there. And yeah, that just the best possible way. Okay, cool. How to make it lexicographically minimum now? So let's write something again. So we'll have 1, 2, then something. Then we arrive at x. We have n somewhere. Let's say x, y, z. So we have to have x there. We have to have 1 here. We have to put something on position x that is not x, because x is on the first position. So we have to put something here, and let's say it's y. So x is a divisor of y, and x is strictly smaller than y. Okay, cool. So what will we put on all these positions? Well, we just put on position p, we just put p. Then again, we have to put something in position y that is not y, because y is already used on position x. And so we just continue to put positions here until we arrive at y and put z there. And again, it should be, z should be divisible by y because of statement. And then we will have to put something in position z, and so on. So in the end, we know that our free number should be n, so we are basically constructing some sequence of numbers starting from x and ending in n. Each one should be divisible by the previous one, So we just multiply x by something each time, but it should still be a divisor of n because we want to end in n. And since we want lexicographically minimum permutation, we know that, well, this prefix is fixed, but in x we want to put the minimum possible number, which is not x. So we choose the minimum number that is divisible by x and also a divisor of n. It might be n, it might be not n, but we have to choose the minimum one because it doesn't matter what happens next. We have to choose the minimum one right now because we are constructing lexicographical minimum permutation. So yeah, we will just put basically x here, 1 here, then on position p, p everywhere, and then we will start with x, and each time we are choosing the minimum number that is divisible by x and also a divisor of n that is greater than x, put it on position x, and then continue until we reach n. Great, cool problem. We should be given n and x, right? If n is not divisible by x, it is impossible. Otherwise, we know that it is possible. We fill in the initial permutation, and then while x is smaller than n, we want to choose the next number. It should be the smallest possible that is divisible by x. We will choose that by just trying only numbers that are divisible by x, and also it should be a divisor of n. We know that we will stop at least at n, so we put y at position x, and then we say that x is equal to y now. They were not lying when they said that it is constructive forces. We again have to construct a sequence of n integers. Each time they should be distinct, and the difference between maximum and the minimum is equal to square root of their sum. Great. So if the maximum is equal to m, then this thing is smaller than m, obviously, but also all of these numbers are smaller than m, so the number under the square root of is n times m, and so the minimum should be kind of close to maximum, right? But it can't be very close because, well, it should be at least n minus 1, right? Because we have to put n minus 2 numbers between them, and they all should be integer and distinct. Well, when you want your numbers to be distinct, we will just build them in increasing order. And one useful trick is to say that instead of defining AI, we will define BI, which is AI minus I. Now B should be not strictly increasing. Okay, so if Bn minus B1 is equal to D for difference, then An minus A1 is Bn plus N. Well, if we have this, then AI is Bi plus I. Bn plus N minus B1 plus 1, so it's Bn minus B1, which is D plus N minus 1. And we want the sum to be square of this number. So D plus N minus 1 squared should be the sum of a's. The sum of a's is from 1 to n, we're saying, is the sum of bi plus I. We can calculate the sum of i's. It's just n times n plus 1 divided by 2 plus the sum of b's. But it is... let's subtract b1 from each element and add b1 n times back. So we will have this. B1 minus B1 is 0. For n minus 2 numbers in between, we will just write what we had. And Bn minus B1, we know that it is D. Okay, why did we do all of that? Why we made our life harder, seemingly? Well, because now we don't care about how that all the B should be different. We care that all the A should be different, and we achieved that by just saying they will be calculated by this formula for some non-decreasing B. But we don't actually care about order of these numbers. So if we choose some numbers, we will just order them. What we care about is that all of these numbers should be at least B1 and at most Bn. So all of these numbers, like after subtracting B1 from them, they should be from 0 to D inclusive. So the sum is actually any number from D from 0 to D times n minus 2. Great. now all we have to do is choose some parameters. Like if we if some number from this interval is okay for us, then we will be able to choose those numbers, obviously, and we will be done. So what looks reasonable? Like, I'm sure that there are a lot of different solutions. Also, we can choose B1. So that's good. Like, we should just make this number big enough, so it should be bigger than this and this. I mean, bigger than their sum. Then we just choose B1 as maximum possible, so that this left side is still smaller, and then just finish here. So we can, for example, say that D is just equal to n. Then this thing is 2n minus 1 squared. It is obviously bigger than n times n plus 1 over 2 plus n even. Well, at least for n big enough. But for n equal to 2, this is 3 squared, and this is 2 times 3 divided by 2, which is 3 plus 2, 5. So yeah, still smaller. So we calculate their difference, divide by n, set b1 to bz, and we know that okay, their difference will be smaller than this number, which is smaller than 2n squared, which is 4n squared. Then we divide it by n, and we get at most 4n, actually something smaller. So b1 is non-negative, but at most 4n, d is equal to n. Then we choose these additions to cover the remainder. And we should be done for all n except for n equal to 2, because for n equal to 2 we cannot choose anything here. But I assume it is given in sample. Yes. Great. Does it actually work? The difference is 2 and the sum is 4, which is square of 2. Great. Otherwise we're saying that d is equal to n. Then we just calculate, let's say it's long. So the this thing is n plus d minus 1 squared. We subtract n times n plus 1 over 2. And we also subtract d, right? Subtract this. Then we assert that it is at least 0. B1 is sum divided by n. Assert that it is, we said that it is at most 4 times n, should be true. Great, then sum is decreased by, well, just remainder modulo n. And now we know that it is smaller than n, so we only actually need to add it to the last, next to last number, so we can just print the answer. So b1 plus I. Yeah, we need to print a's. We have chosen b's, so we add in I back. And then the next one is b1 plus sum plus n minus 1, and the last one is b1 plus d plus n. Six, 8, 11. The difference is 5 and the sum is 25. Great. 9, 10, 14, 16. The difference is 7 and the sum is 49. Looks good. Okay, so there is some weird story, but actually, like, we have grid n by m. The sum of n times m is bounded by something. We also have number h, and we leave modulo h. So we have the grid. Each cell of the grid should have a number from, well, the remainder modulo h. Some numbers are given to us already, and some numbers are not, and we can put anything we want there. We are asked to calculate the number of ways to put the numbers there such that the grid is solvable, and by solvable they mean that it is possible by doing operations like choosing some row or column and do plus plus to all the elements of that column. And we want to achieve the state in which all the numbers are the same. If we achieve the state in which all the numbers are the same, we can obviously achieve the state where all the numbers are zeros, just for each column do plus plus until we reach 0. And the order of operations doesn't matter, so what matters is how many operations we will do for each row and each column. This sounds like a well-known problem. Don't think they should have put it in the contest. Okay, so we want how to check that the table is good. The table is good if for all ij, ai plus bj plus cij is equal to 0 mod h. Okay, so we can rewrite it as ai plus bj is equal to minus cij mod h. And when you have such a structure, basically one of the methods that helps in some of the problems about grids is to consider it as a graph, actually a bipartite graph with n plus m vertices. One part is responsible for rows, one part is responsible for columns, and the cells of the grid are responsible for edges. So what can we understand in this case? Well, if we know Cij and we know Ai, then we will be able to figure out what is Bj. So if we look at the connected component, if we determine what to put in one of the vertices, then we know what to put in all the vertices we can reach by our edges, by the edges that exist. We can get some contradictions if we have a cycle which is bad. But this is kind of similar to how you would check the graph for being bipartite. Basically, just run DFS, you put something, for example 0 in one of the vertices, then you run DFS and calculate the values for all the other vertices in this component. And if we, like when traversing an edge, we already know what on both ends of this edge, we just check that it is correct. If it is not, then it is unsolvable, so the answer is just 0. Otherwise, we will restore the whole component. What we need to be careful about here is to, well, how to calculate the answer, and we need to remember that the answer is not the number of ways to choose A and B. The answer is the number of resulting tables, and well, each table, when we know A and B, the table is defined uniquely. We know Cij from this for each cell. But we can get the same table for different values of A and B. For example, if we add something to all of the A's and subtract the same number from all of the B's, we will get the same table. But basically that's the only way to get the same table. If we change A1 somehow to stay in the same table, if we add some D to A1, then we have to subtract D from all the B's, then we have to add D to all of the A's. So the number of tables is actually the number of ways to choose A and B divided by H, and the answer is just H to the power of number of connected components minus 1. Or 0 if there is a contradiction. This is a very well-known problem. It should not appear in the first contest. Very bad coordinating. Alright, why the answer is H to the power of connected components? Because for each connected component we put 0 somewhere, then we restore everything. If we increase that 0, then decrease everything in the other part, but in that connected component by the same amount, but increase everything in our part in this component, we will get different way to assign A and B. For this connected component there are H ways. So for each connected component we can get H ways, they're independent, so it's the number of ways to get A and B is H to the power of number of components, but we then have to divide it by H back. So I'm reading the table. If the number is not known, then we don't do anything. Otherwise, we have to add the edge. It's undirected, so we add twice. The edge between vertices x and n plus y. n plus, because, well, the vertices from 0 to n not inclusive are the first part, and from n to n plus m is the second part. And, well, I want to say that the sum of those values is z. It's actually minus z, but multiplying everything by -1 doesn't matter. So, so yeah, I'm just making my code harder to understand for no apparent reason. Traversing all the vertices. If it is not used yet, we put 0 there and run DFS from it. If not DFS, just print for 0. Otherwise, it's plus plus, then it's minus minus, and we just multiply it by h unstems. Well, yeah, I guess I have it pre-written. So it's amount of h to the power of DFS dot x DFS of v. So we know that the number on the other end should be the number written on the edge minus our number. If we don't know the number on the other end, we say that, okay, now we know that it's x, and run DFS from there. Oh yeah, and if not DFS, return false. Otherwise, if it is not true that it's x, just return false. Otherwise, return true. And the last problem, assuming I got E accepted. Is accepted, at least on pretests. And problem F. We will be working with binary strings. The binary string is called decent if it has an equal number of zeros and ones. Initially, we have an infinite binary string whose characters are all zeros. We then have to process some updates, at most 200,000 of them, which just flip one bit. We need to keep a set of disjoint ranges such that each range represents a decent binary string. Like the substring corresponding to that range is a decent binary string, and it covers all the ones. Makes sense. You only need to output the ranges that are added 2. Don't care, I guess. Well, we only need to output the changes, and the total number of changes should be most 10 to the power of 6, which probably means like 5n. And I think it is 5 and not like log n divided by 3 in this particular case. Well, it seems that it should be doable in a linear number of changes. Okay, but ranges can be anything I want. They can be long, right? Well, they can be very long, but that doesn't matter if all the AI is small. Great. Okay, this is not very great. Like I cannot go to the left. Well, okay. So how do we want to understand that? Like, instead of thinking about binary string, I probably want to think about like ones and minus ones. So basically, I will change the symbol c to -1 to the power of c. So 0 becomes 1 and 1 becomes -1. Then I will maintain the prefix sums, and the substring is decent if it has 0 sum. So the prefix sums on its end are equal. When we change one symbol, we either change 0 to 1, which means we change 1 to -1, which means that we do -2 in point, which changes all the prefix sums on suffix by, like, decreases them by 2. We change from 1 to 0, does the opposite, it increases them by 2. Is it like interactive? No, and it is offline. Like all the changes are given to us beforehand, and we need to construct one solution. Like we don't have to process everything online. Although I feel like it should be possible. Okay, I guess for the first time in this contest, I don't know what to do. Okay, so if I have a good string, it's a good rate, like I have 5 ones, 5 zeros, and then 1 is changed to 0. This is changed to 0. I feel like I should be able to split it into 2 good strings and just left out 2 zeros. How am I going to do that? I am going to say that, well, now I know that the number of zeros is greater than the number of ones by 2, and if I do the thing I was talking about, say that 0 is 1 and 1 is minus 1, and draw prefix sums, it will look like this. It's 0, 1, 1, 0, because I changed it. 0, 0, 1, 0, 0, 1. And yeah, I will always arrive at 2. And I should be able to find I actually need like 2 consecutive zeros. Well, if I want to split it into 2, yeah, I need to choose the zeros I want to left out, this one and this one, and I will have the segments. But actually, I could have had like 1, 0. I need these 2 to be neighbors. It should be possible, right? Like if I have 0 that increases the balance from 0 to 1, then if after it I have 1, then I will go to 0 again, and that's fine. So I need to find, basically if I find the first place where I get balance 2, then I had 2 zeros here. because if it was 1, then I decreased, so I had balance 2 before that. So if I find the first place, yeah, there will be 2 zeros here, and these 2 segments are good. They're covering all the ones, and that's great. Okay, so if I had my solution and then 1 was changed to 0, I should be able to rebuild it. And since I'm removing this segment and adding 2 new segments, I'm doing 3 operations, which is good. The only and I'm adding segments like inside this one, so they can't intersect with any other segments because they didn't intersect with this big one. Okay, now to the other part. If I have 0 and it's changed to 1, I guess there are like different situations possible here. If that 1 was outside of all of my segments, so I had like segments, then I have 0 here, and then I have segments. This 0 is changed to 1. If it has neighboring 0, then we can just create a new segment, but like it can be sandwiched between 2 of my segments. That probably means that I should remove those segments and rebuild everything. I know that everything outside my segments are zeros because I had to cover all the ones. That's great. And I also feel like I should be able to maintain the property that I don't have 2 segments back to back. Because in that case, I can change those 2 segments to 1, like merge them. That requires additional operations, but it decreases the number of segments. So up until now, in the first part, I only used 3 operations. So if we can say something good about, maybe it amortizes somehow. We also know that the number of adding ones should be not less than the number of removing ones, so maybe that also helps. But for now, let's not really care about fitting in the limits. Just let's say that I'm maintaining the properties that between every 2 segments from my construction, there is at least 1 0. There might be some problem like that. For the leftmost segment, it is possible that there is no 0 to the left of it, but it should be fine. Just I have to think about that. I can't just assume that I have zeros everywhere. But yeah, if that 0 had a neighboring 0, we can just create a new segment and be done. Maybe we'll have to merge something, but that calculating the number of queries is not that important right now. So the other case is that like they're sandwiched, right? I have 0 here, and I know that I have 0 here. Well, okay, when I change this 0 to 1, this segment is good now, right? I had 0 balance here, 0 balance here, and I add 1 and 1 0. So I just remove these two segments and this one may be merged in something else. Great. Yeah, maintaining that property shouldn't be a problem because like I won't actually like remove two segments and add one use and remove it back and remove the next one and merge. Like that shouldn't happen. We can just check that all of the operations maintain that, like the removal of one maintains the operation, the property that there are no two segments back to back. Okay, so the last case, and here we will spend like 4 operations. If there is a segment right here, we will have to remove this, and then create one big. The last case is 0 inside one of our segments. That should be easy for the most part, right? I change this 0 to 1, but I know that I have 0 here. It's not enough to just add it, but if I have 2 zeros here, it's enough. So if I have 2 zeros here, I will just remove this segment and this one may be merged with the next one. If I don't have 2 zeros here, it means that I have another segment here, but after it there is a 0. So this segment is good now. And maybe I need to merge it with the next one. So I should be able to do everything. And each time I spend at most 4 operations, right? And like here I spend 3 operations, and here I spend 4. Great. That sounds like a solution. I actually spent only 4 and actually like smaller than that because reasons. What is the actual number of queries I will spend? Like if I have m queries that remove 1, then I have n minus m queries that add 1. I know that m is at most n over 2. And it seems not helpful because like for this query I only spent 3 and for this I maybe spent 4, but only this kind of query, well, okay, this kind of query increases the number of segments by 1, and when I have like 0, like two zeros back to back, and I change one of them to 1, I will create a new segment, but that is done in just one operation. So basically like for this, I always spend 3 queries, so it's 3m. Actually, not always, like one of those 2 segments can be empty, but let's say that it's 3m. And when I add one, I spend 1 query to add a segment. And also I spend some queries to remove a segment, but okay, let's just calculate the number of additions actually. Like for this query I add 2 segments, I remove 1 and add 2, and when I add 1 I always add 1 big segment. So the number of additions is bounded by n plus m, right? N minus m plus 2m, which is bounded by 3 over 2n, because m is bounded by n over 2. And we can remove a segment only if we added it before, so the total number of operations we will do is bounded by 3n actually. That's great. Let's implement that. And like it is fully online. I didn't use the fact that I'm given all the operations before, and despite the fact that it is amortized to 3n, I know that every operation, like every query makes only 4 operations at most, so it's obviously not more than 4n, but it actually amortizes to 3n. That's great. Okay, so what do I need? I probably need to maintain the set of all the segments I have right now. I can just maintain the string. I can maintain the set of positions of ones if I want to, but I don't think that I actually want. And I actually will just always move to the right. Yeah, that should be actually really simple to implement. So I have some queries. Okay, so if it is one, then I want to find the segment that covers it. Actually, I will find The next one, so I know that the left border should be at most P. So yeah, it shouldn't be the begin because I know that there should be a segment that covers me. So I can assert that it actually does cover me. How do they print segments? The leftmost and rightmost point covered by the segment. Okay, I will obviously store half intervals. So this is the leftmost point that is covered, and this is the rightmost point that is covered plus 1, the first point that is not covered. So yeah, we assert this. Oh right, I need to find this place, which is not great. I mean, I can implement some kind of segment tree. And it looks like I will have to. Do I really have to implement the segment tree? Pom, pom, pom. Well, okay. It doesn't make sense to spend so much time on that decision. If I can't see anything simpler right way, it probably means that I should just implement it. It's not that hard. I will spend more time on choosing if I should do that, which is not great. So what I need from segment tree, I want to store prefix sums in the segment tree, so I need to add on suffix, so add on segment basically, and I want to do what? I want to find the leftmost point with given balance. It would be hard in general, like find the leftmost point with given value in segment tree, but I know that all of the values before that on this segment have smaller balance, so I need to find like the first place where maximum is greater or equal to that balance, and that balance is balance in this point plus 2, or like balancing this pool. Yeah. Okay, so I will do that by finding the leftmost point and so on by descent on the segment tree. So I don't need to store like the positions. I just need to store the value and to be able to do +1 segment. Great. I will need push annotate. Come on. What else do I need? I need to get value in point to get the balance I want to find. But like getting value in point is basically max on segment, but just that segment is of length 1. And it is not much simpler, so I will just write get max. I'm starting with zeros, but yeah, I need infinite. Don't forget to push and return max from 2 sons. So get point is just get max when we need this one. Cool. and I need like find leftmost greater. Oh, it actually will be not lesser, greater or equal, but that's too much words. I don't care about the right border of the segment because like I know that there will be someone on my segment that is okay for me. So I only need to care about the left border. So if my value is smaller than x, that's bad. Like I know that nobody in my subtree can be good. If L is greater or equal to my right border, then it's also not good. If my left border is no, that doesn't matter. If I am a leaf, then I know that my value is at least x, and at least one position in my subtree lies on the suffix we want, but there is only one position in my subtree, so I'm good. This is just the answer. Otherwise, I'm not a leaf, so I have to push, not forget about that. And then I will try to find leftmost greater first in my left sum, because it's more to the left. If it's not -1, so I find someone, then it's the answer. Otherwise, I have to then find it in my right sum, and that still works in logarithm time because, well, these two things basically do the query as usual on the segment tree, so the complexity is fine, and I like this way of writing the descent on segment tree because it is the same as I write everything on segment tree. Like before I came up with this, it was like kind of a hassle to write something that is correct, but that works. And well, it wouldn't be much harder if I had a segment actually, but well, basically this check should be as always, like if my segment doesn't intersect with query segment, then it's bad. Okay, so now I can find the leftmost position. Cool. Okay, so don't forget to call build. So when I do this, alright, I need to initialize everything, right? Like I have zeros everywhere, but like zeros are actually ones, and I want prefix sums, so the value in position I is actually I, because like it's prefix sums of I ones, and I need to push it up the tree, basically call update I. Great. Normally I would do that by just like add 1 in each point, but I had too much experiences when like this get cost time limit because well that is n log n, and like it shouldn't be a problem because like the main solution is also n log n, but it's like suddenly 2 times slower, and I'm getting time limit, so I'm initializing in linear time now. Usually shouldn't be an issue in this problem, but I think there are like 5 seconds, but okay. So yeah, now we need to not forget to actually do queries to segment 3, add on segment from, so if I'm in P, then sums from P plus 1 to infinity are decreased by 2. Increased by 2. And here they will be decreased by 2 because I change 0 to 1. Actually, yeah, let's just change it right now. So back to this part. I found the segment. It's good. Now I saying that I want the balance in my left border. Then I want the position that is the leftmost position right to the left border of my segment with balance greater by 2, and I want to remove cut out the segment of length 2 between those two. So what I'm actually doing is I'm saying remove segment from I will not do this here. Remove segment, just a second, add segment as first pos minus 2 and add segment pos as second. One or both of those segments could be empty, but I will just handle this in this function. Great, we are done. Let's write these functions. They're really simple. Add segment left right, assert that if it is empty, then just don't do anything. Otherwise we need to insert the segment and output it. I guess I will have to calculate the number of iterations, right? Or no? Alright, number of ranges to be removed and then added. Oh, come on. Okay. So I can't even write it. Like I can't add segments and remove it at the same time. Now, okay. Let's store to be added and to be removed, and after all of this we will print what is need to be done and clear those vectors. Okay, cool. So we don't print anything here. Instead we say that to be added this one. Push back. Wait, segment, the same thing, short sequence find not equal to end, race and to be removed. Great. Push back again. Cool. So, here I'm changing 0 to 1. I want to find the next segment from this point. I know that B shouldn't be covered, so well, let's not throw a third here. It's just hard to implement. Okay, so if I don't have anything after me, so this iterator is equal to end, or it is too far, first is at least, well, let's say greater than t plus 2. So like if it is too far, I want to add p plus 1, but I may have to merge it with someone before me. Well, okay, let's say that we will have our segment that we will want to add. Now it's pp plus 1. So if this happens, and actually I can say greater or equal now, I will call like try add this segment, and I need to change this segment to pp plus 2 actually. Try add, what will it do? So try add will find the segments that touch this one, remove them, actually like by calling remove segment, and change as. Then we'll just call add seg as and be done. But I can't write continue. I would love to, but I can't write continue because I need to like, output something actually here. The time is running. Okay, we need to speed up a bit. Yeah, it's first, second. Oh yeah, that is not useful. Great. Otherwise, I know that sort first equal to p plus 1, and I know that it exists. So I will well, I will remove it. Well, yeah, I will just say that my right border that I want is second plus 1. Like I want to get the next 0. Then I will remove this segment. Then I will try add my segment. Maybe it will be merged with someone, and then I will actually add it. Okay, so I call it like that. So instead of try add, just add, I guess. Add with merge. Okay, and I will have to print the answer. First, I need to print all the segments that I want to remove to be removed dot size, and then print all of them. One by one, I guess. -1. Then the same with segments to be added. Come on. I'm kind of in a hurry here. To be added. First, second, -1, and print empty line, right? I'm not sure it's necessary, but yeah, and we have to clear, to be added, and to be removed. Great. So what's left is add with merge. Add with merge. So we want to add the segment from out to R, but we may need to merge it with something before that. So we will call lower bound. If it is not and the left border of the segment coincides with our right border, we're saying that our right border is now the right border of the segment, and we need to remove it by calling rem segment, not just remove from set. Again, call lower bound because we might have changed something in the set. And now if it is not begin and previous one has a right border equal to our left border, then our left border is its left border, and we need to remove it. And then add the segment. It's compiled. Insane. So we're not removing anything and adding 1, 2, not removing anything, adding 6, 7, removing 6, 7, adding 5, 8, removing 5, 8, adding 5, 6, interesting, removing 5, 6. Not very interesting sample, but let's submit, why not? Why not? Well, because it doesn't work. Okay, let's just read at least once. I have like 9.5 minutes. Great. My segment 3 should be bigger. That's probably not on cancer 2. Oh, I forgot about the case when 0 is inside. What I wanted to do in that case. So yeah, I'm finding if it's not begin and contains our point, else everything else. So so I want to erase this segment, and then 2 times I want to add 0, maybe merge. Okay, so yeah, this is not good now. Okay, I will rewrite it. I have 3 minutes, that's great. So remove segment, then 2 times. I want to say plus try at. Yeah, and that just at sec. Great. So here try at and then at, and the same here. So try at should do this and not do this. So I have 2 minutes. Run time 5. This is bad. This is bad. This is really bad. Plus 1. Well, I don't really have time to find more bugs, so yeah, we can just update the page. Interesting. Less than 10 people got F accepted. Yay, pretests passed. I managed to do that. Thanks for watching.